Hello, welcome to this lecture. In this lecture, we shall discuss the singular value decomposition and how it is applied to image compression. So the lecture is supposed to be a simplified introduction to singular value decomposition. It is good if you already have some basics of linear algebra and matrices, but we'll try to make it as accessible as possible, even if you don't have this background. The application to image compression will be illustrated using a software called Octave, software which is freely downloadable and uses the same commands as MatLab. So we'll just dive in and start. So we first look at some basics of the n-dimensional vector space, Rn. We give some definitions. A set of vectors is linearly independent if none of them can be written as a sum of multiples of the other vectors, or none of them can be written as a linear combination of the other vectors. We shall mostly work in this case with n is equal to 4. The same ideas can be extended to larger values of n, but for the sake of simplicity, we shall just work with n is equal to 4 or smaller. So if we have a set of 4 vectors in R4, the set will be linearly independent if any vector in R4 can be written as a linear combination of this set of 4 vectors, and this set must also be linearly independent. Any other basis will have the same number of elements, and if you add any one more element, the set would no longer be linearly independent, and if we remove even just one element, the set will no longer span R4. In other words, some vectors, it will not be possible to write some vectors as a linear combination of the remaining vectors in the set. The scalars alpha 1, alpha 2, alpha 3, and alpha 4 will be called the coordinates of the vector v with respect to the given basis. And we can have several bases. There are infinitely many, though some are better than others, as we shall see. So two vectors are orthogonal if their dot product is 0. This is the similar to what we know as perpendicular in the 2-dimensional and 3-dimensional spaces. The two vectors are perpendicular if their dot product is 0. And we can have a basis which we call orthonormal if each vector has unit length and the vectors are pairwise orthogonal. So this means that any two vectors that you pick in the set will be orthogonal, or if you like, you can use the word perpendicular. Any set of linearly independent vectors can be extended to form a basis of R4. So if I have two linearly independent vectors in R4, there are ways of extending that to a total of 4 linearly independent vectors which form a basis for R4. Now if the basis is orthonormal, I can also extend it to an orthonormal basis. Orthonormal bases are very nice for our work and for reasons that will become apparent. One reason is because it's very easy to compute the coordinates of a vector when you have, with respect to a basis, when the basis is an orthonormal basis. So mostly we shall work with the orthonormal basis. We now look at the concept of matrix decomposition, and you may be familiar with the eigen decomposition of a matrix, where you can factor a vector as a product of V multiplied by D multiplied by the inverse of V, where D is a diagonal matrix and if A happens to be symmetric, we can make it better. We find an orthogonal eigen decomposition where V will be an orthogonal matrix, and then computing the inverse is just as simple as getting the transpose of V. Now, this decomposition is only possible for square matrices, and not all square matrices. There are some square matrices also which will not have an eigen decomposition. We will not get into the details of that, but it means there are some that are left out. So we are going to look at the options that the matrix that are left out have, and these options work even for all the matrices, whether they are square or not, or whether they have n linearly independent eigenvectors or not. The option is universal. So let's see what happens. What happens when you multiply a vector by this square matrix? So we'll work with a 4x4 matrix and a vector in R4, and when we do that, multiply A by V. A is the matrix and V is the vector. We get another vector in R4, probably in a different direction from V. So we can get a unit vector in the direction of the image under this matrix multiplication, and then the new vector can be written as a multiple of the unit vector multiplied by the length. So it's a unit vector multiplied by the length of the image vector W, and so U is just a unit vector in the direction of the image vector. So we can illustrate this in the diagram. You can see when we multiply A by V, we can think of this as a 2x2 matrix. In the two-dimensional space, we multiply A by V, we get a new vector W, which is in a different direction from V and maybe longer or shorter than V. In this case, it is longer. So we can see that we can write this new vector W as a multiple of the unit vector U, which is in the same direction as W, so that AV, we use the coefficient, we call it sigma. So AV is equal to sigma U, and we shall use sigma for the rest of the discussion. So now we move to the details of the singular value decomposition. Here you will have to take a leap of faith and believe that it is possible to have two orthonormal bases satisfying following conditions, so that AV1 will be sigma 1 U1, AV2 will be sigma 2 U2, A3 V3 is mapped to the 0 vector and can be written as 0 multiplied by U3, and AV is also mapped, AV4 it's also mapped to the 0 vector and therefore can be written as 0 times U4. Here we order this in such a way that sigma 1 is greater than or equal to sigma 2. So we set up a matrix V whose columns are the vectors V1, V2, V3 and V4. And we also set up another matrix U whose columns are just the vectors U1, U2, U3 and U4. So we have two 4x4 matrices. Now, since the bases are orthonormal, these matrices will end up being orthogonal, and therefore just to get the inverse is as simple as getting the transpose. And they are connected as follows. If you multiply A by V, it should be equal to U multiplied by sigma, where sigma is the matrix shown with the leading diagonal having sigma 1 and sigma 2 as the first two elements and zeros everywhere else. So this is the point at which now we can proceed to factorize the matrix. Since we know V is orthogonal, we can post multiply both sides by V transpose so that we get the decomposition. We shall see that in a short while. Now, this is the setup. V is a 4x4 matrix, and these columns are the vectors V1, V2, V3, and V4, and these are the vectors V1, U1, U2, U3, and U4. And we can write the product of A and V as seen here. This is a matrix N, that's the matrix V, and all this is equal to UV. Again, U is written here. U sigma, sorry, it's equal to U sigma. So we have U here and we have sigma here, the same sigma that we saw in the previous slide. So we can post multiply both sides by V transpose so that we now have A is equal to U sigma multiplied by V transpose. And now this is what we see on the slide. In full form, we have U here, we have sigma, and we have V transpose. Here you will notice that the rows of V are now the columns of V, because we have taken the transpose of V. So this is V transpose. So we don't really need to have the full 4x4 matrix, because if we can just go back to the previous slide for a minute. In this multiplication, we notice that the last two rows of sigma are zeros, and also the last two columns of sigma are also all zeros. So it means we can delete the third and the fourth column of U, and also delete the third and the fourth row of V transpose, and lose nothing because they contribute nothing to the final sum. They will all be multiplied by these zeros and they don't contribute anything to the final matrix. If we drop them, we will still have a matrix, a complete matrix multiplication that gives us A. So that's exactly what we've done here, so that the thinner version of the singular value decomposition will now be this 4x2 matrix multiplied by this 2x2 matrix multiplied by this 2x4 matrix, and it still gives us the same answer. So we can now expand this thin version and write it in vector form, or as a sum of smaller several matrices. So the first matrix will be this U1 multiplied by V1 transpose. So U1 is this vector, and this is V1 transpose. That's what gives us the first matrix. The same with the next one, U1. This should be U2 multiplied by V2 transpose. This is a mistake. That should be U2 multiplied by V2 transpose. V2, the vector in the second row here, and U2, the vector in the second column here. And each will be multiplied by sigma 1 and sigma 2. So remember, we had ordered this so that sigma 1 is much greater than, or is greater than or equal to sigma 2. And if it happens that sigma 1 is much bigger than sigma 2, we can omit this second part of the sum and just write A as sigma 1 multiplied by A1, and this will give us an approximation of A. So this is a singular value decomposition now, and we have considered this for the case of a square matrix, and now we want to consider this for the case when the matrix is not square. So here we shall assume the number of rows are more than the number of columns for the matrix. So M is greater than or equal to N. If we have the opposite, we can just work with the transpose of a matrix and still end up with our decomposition. So we pick a 4x3 matrix, and anytime you have a 4x3 matrix, you can multiply it by a 3x3 matrix to get a 3x3 vector, or a vector in R3 to get another vector in R4. So it will be more of a transformation or a map from R3 to R4. So for that reason, we let's pick 3 vectors which form an orthonormal basis for R3, and for each of these vectors we have the following situation. Let's set up a v1 to be equal to sigma 1 u1, a v2 will be equal to sigma 2 u2, and a v3 is mapped to 0, so it's equal to 0 multiplied by u3. Now u1, u2 and u3 are vectors in R4, and we again here you'll have to take a leap of faith and assume that they form an orthonormal set. So they are not a basis, but they form an orthonormal set. And we also have that sigma 1 is bigger than or equal to sigma 2. So with this relationship set up here, we can again write in matrix form as follows: AV is equal to U sigma, where V is a matrix whose columns are the vectors V1, V2 and V3, and U again is a matrix whose columns are, U is the matrix whose columns are U1, U2 and U3. So since the vectors form an orthonormal set, this matrix V will be an orthogonal matrix with the transpose V equal to the inverse of V. That means we can post multiply this equation here in the third bullet by the transpose of V to get A, and also multiply the right hand side here by V transpose to get U sigma V transpose. So this gives us a singular value decomposition of A, which is not square. So this is illustrated here, and we can see the complete multiplication here, where A is equal to, we have a we have U here, we have sigma, and then we have V transpose here. So we can rewrite again this expansion as a product of as a sum of matrices as follows. So A can be written as sigma 1 U1 V1 transpose, sigma 2 U2 V2 transpose. For this example up here, you'd have to stop at U2 because there are only two non-zero values here, sigma 1 and sigma 2. But if you have more than, it's a larger matrix and you have more than two non-zero values for sigma 1 and sigma 2, then you can extend this multiplication up to the last non-zero value, which we can call sigma R. Now they are ordered in descending order, so that if we can pick a few of them which we feel are large enough, and we can get an approximation of A. So we can take the first k values of sigma 1, sigma 2 up to sigma k, and get an approximation of A by stopping this sum at the point sigma k u k v k transpose. So now these vectors in the matrix U are called the left singular vectors, and these vectors which form the columns of the matrix V are called the right singular vectors, And these numbers, sigma 1 and sigma 2, are called the singular values of the decomposition. So those are the terms we shall be using. So we can see that it works for both square matrices and matrices that are not square as well. And in this case, we have a 4x3 matrix here, which can be extended, and also that would force us to make this matrix sigma a little bigger. And let's see how that works in the next slide. So again, we notice that we have only two non-zero values, sigma 1 and sigma 2 here. But if we look carefully, again, we notice that the last row of sigma is 0. The last column of sigma is also all zeros. So we can drop these two rows and these two columns. You can drop this row and this column, and at the same time drop this column, the last column of U, and the last row of V, and we don't lose anything, and then we have a thinner version of the decomposition. So this is what happens, and that would be the expansion in terms of matrices. So we have A as a sum of two matrices. So this would be the first matrix, that would be the second matrix. And we can now extend the same ideas to a larger matrix which has R non-zero singular values, and this is what it will look like, again with all the singular values ordered in descending order. And again, this is just a repetition of the approximation of A. We can get a value of K smaller than R and get an approximation of A. So this is assuming that all the other values are so small that they don't contribute much to the values of the entries in A. So we check if our approximation is good by looking at this ratio of the sum of the first K singular values divided by all the singular values. So this will tell us how good our approximation is, the quality of our approximation. Now, as seen earlier, anytime you have a set of linearly independent vectors, you can extend it to a basis. So the vectors u1, u2, and u2 are orthonormal, and by extension they will be linearly independent. We can extend that to an orthonormal basis of R4 and now form a new matrix U, a bigger one, where you have one extra column rather, that we didn't have. So this U4, this vector U4 becomes the fourth column of U. And then we can extend sigma in our expansion was initially was a 3x3 matrix. So we can add one row here to make this a 4x3 matrix. And then now our expanded SVD for a matrix which is not square becomes this. We have the 4x4 matrix here, and the 4x3 matrix here, and the 3x3 matrix here. So this is a full SVD, though we don't need it because we can actually drop these two columns and we can drop this third row of V. So we can drop the two columns of U, we can drop the last two columns, or last two rows, of sigma, as well as the last. We can drop the last two rows of the matrix sigma, and we can also drop the last column of sigma, as well as drop the last row of V. We don't need those. The matrix will still work without those, and we save some space when we drop them. But this is just to show that you can work with the full version. You can get the full version as well. So a matrix, usually an image in the computer, usually stored as a matrix, and usually you want to use as little space as possible when you store the image. So it helps if you can compress it and make it smaller. So this concept of singular value decomposition can be used to compress the image, because it is just stored as a matrix. And so in this case we can have if A is equal to this expansion. Suppose this is a full decomposition from sigma 1 up to sigma r. Suppose these are all the non-singular values. Sorry, suppose these are all the singular values of A, and we pick a value k that is less than or equal to r, preferably less than, strictly less than. Then we can get an approximation of A by stopping at k, the sum at k, like this. So this approximation can be written in matrix form as follows. A will be approximately U consisting of the first k columns of U, and sigma is just the k. Sigma k is a k by k matrix which is diagonal, and the diagonal entries are just the first k singular values, and vk is also consisting of the first k rows of V transpose. Just pick the first k rows of the transpose of V, and we get an approximation of A. So we can do this decomposition and then use this as an approximation of the image, which will enable us to store fewer numbers and save space on the computer. So we will eventually have less numbers to store in the computer, and we occupy less space on the computer. Rather, the image occupies less space on the computer. So here is an example of a singular value decomposition of a matrix. So the matrix is given here, it's equal to A. But this is just a full decomposition. We have 4 by 4 matrix here, then the 3 by 4 by 3 matrix sigma, and the 3 by 3 matrix V. So this is V, that's sigma, and this is A. Now you notice we can actually drop the last 2 columns of U, this first matrix. We can also, in this case we can drop the only one column, the last column of U. We can drop the last row of sigma, and we can't drop anything in V because we need all the 3 rows. It is, unless if we had a 0 column here, that's when we'd be able to drop any a row in V. So this gives an example of decomposition, singular value decomposition of a matrix, a 4 by 3 matrix. So an image consists of pixels. This diagram here sort of illustrates what an image is made up of. So these boxes would be the pixels. They will not be this large, because if they are this large, then the image will be what we normally call pixelated. So but this is supposed just to illustrate that each box here will represent a pixel. So on each box will be assigned a number between 0 and 255, and therefore you'll have a matrix here full of numbers. Now if it's a black and white image, this will just be one matrix usually. If it's a colored image, it will be made up of 3 matrices, the red, green and blue. Each layer will I have will be a matrix for the red layer and the green layer and the blue layer separately. So we shall use software called Octave to illustrate this image compression. Octave is free and uses exactly the same commands as MatLab. I intended to use R initially, but there's a package called EB image that gave me trouble. I was not able to install it in good time, so I opted to work with Octave. Maybe once I get that fixed, I can also do another one in R to show how this can be done in R. There are better algorithms for compressing images, especially the Fourier transforms. The Fourier transforms, usually the discrete Fourier transform, is a better way of compressing images, but this algorithm of the singular value decomposition also has other benefits. It can be useful in image recognition. We shall not look at image recognition now, but we'll just look at the image compression. But the same ideas can be expanded to many other things. It's a very versatile technique. It can be used in so many ways. It's a very powerful technique. So here is an application of this compression. So if you look at these images, this is an image of an apple tree, and you can see I think the image was about 1000 by 750. So that means if you do the singular value decomposition of this matrix, you should have a total of 750 singular values. So if we pick just the first 20 out of 750, you see we already have a fairly, still a bit fuzzy, but you can get the outline of the tree. You can't see the fruits very clearly, but you can get the general outline of the tree. So this is not a very good quality image. If we increase the rank to 40, that means we pick only the first 40 singular values. Then we can now see some spots. These white spots are the apples. And it gets clearer as we increase the rank. At 80, it's much clearer, and at 150, it's very clear. So with just 150 out of 750 singular values, we still have a full, very clear picture. And we can easily drop the remaining 600 singular values without losing much. Thank you. And now we shall move to the live demonstration of image compression using Octave. So here now we have fired up Octave. It's open. I've already set the working directory to the directory which contains the image that we are going to compress, so that works better. So we will just go ahead and open the M file which has the code for this. So I'll go to file, open this. This is a file that has the code. Okay, we can make the screen a little bigger. There it is. So this is how we're going to do this. I'll run through the code and describe what the different blocks are doing. Then after that we'll run the M file and then go through the output one by one. So the first line is just loads the package that we need for the analysis. This is the image package. So this first line is just to load the image. So the third line brings in the image. The image is the apple tree that you saw in the presentation. It's a colored image, and we shall convert it to grayscale so that we can just analyze it as one matrix. So this next line 7 displays the original image, the colored image. Then we move on to line 11 to we don't need this. So line 10 to 13 pulls out the three different frames: the red frame, the green frame, and the blue frame. Because it was a color diagram, we get to see all the three different frames, though we shall not use them. One way would be to pick each frame and run a singular value decomposition on each frame and put them back together again to form the compressed color image, but we shall not do that. Now this simply displays it's going to display the RGB frames, the red, green and blue in one plot. So we go all the way up to that point where this last one is displaying the blue frame. So the next line of block here will convert the image to a grayscale image and then display the image here. This line number 37 will display the grayscale image. We have given it a title. Now the size of the image will be 1000 by 750 pixels. Okay, then we put the image, since it's a matrix, we convert it into double number format. Once that is done, we run the singular value decomposition command SVD on the matrix. So the output will be U, which is made up of the left singular vectors. Sigma is a matrix which contains the singular values as the diagonal, and V will be the matrix which contains the right singular vectors. So this command will do it all at once, and it will be stored in these three variables. U will be stored in this capital U, sigma will be stored in this sigma, and the matrix V will be stored in this capital V. So the next step is to try to obtain an approximation of the image. So we use the first 30 singular values, and then we also display the rank 30 image. So if you notice in line 51, we have to convert the matrix back into the unsigned 8-bit integer. This UINT8 converts the matrix back into the unsigned 8-bit integer. If you don't do this, the image will not display properly. Then the next part is to display. We display the rank 30 image. Yes, now we display it in the next part between line 55 and 56. Then the next part simply plots the, I think it's called the scree plot or something, the cumulative sum of the singular values plotted on a graph, so that we can get to see how good our quality, how good our approximation is. So that helps us to check how good the approximation is. We shall see the diagram. So the next bit generates 4 different approximations: rank 20, rank 40, rank 80 and rank 150. That is done through this for loop, and then all those 4 images are displayed in one plot. So now I'm going to run the program. Then we shall go through all the output one by one. Takes a bit of time, so we'll just wait it out. There. I think now that's the last output. I'll just maximize this. So let's look at the diagrams. So we can see the rank 20 is not so. This is a final one which did the 4 different ranks. Rank 20 is not so clear. We had already seen this in the presentation, and it gets clearer as we increase the rank. At a.k.a. it's reasonable, good enough to see everything. We shall go back eventually. We shall see what the original picture look like. So I'll close this. Now this one shows a cumulative sum of the singular values as you go along. So this counts the number of singular values. We get up to around 750. There should be a total of 750 in total. But we can see that at just about 200 we have over 80%. This is 0.8, over 80% good information. At around here, I can't tell what this is. Maybe I should have made the scale better. But you can see with a very small quantity, maybe about 40, I don't know, 20, we have almost 50% of the information without having to consider all the other singular values. So this will help us just tell how the quality of our approximation. Then this is the rank 30 image that we started with. You can see again at rank 30 it's not so clear. You could try this for lower ranks and see what happens. You just use the same code and change the rank to 10, say, and see what happens, or 5 and see what happens. So this is a grayscale image of the original image. The original image was colored, and after converting it to grayscale, this is the original image. You can see this is very clear because it's the image exactly as it was imported into Octave. So I'll close this again. Now these are the frames. These are the 3 different frames for red, green and blue. The spots that have more red in them would be brighter here in the red frame. The spots that have more green in them would be brighter in the green frame, and so on. This is, if you want to see this better, it's best to do it on a diagram that, or rather on a picture that has 3 different purely green, purely red and purely blue sections, and one maybe that has a mix. If you put them all on the same plot and run the same separation of the frames, you will be able to see that a little better. And this is the original colored image which we converted to grayscale and did the analysis. So thank you very much for watching this, and if you found this useful, please subscribe to my channel, and we'll be doing more to talk about how this can be done for image recognition. Please subscribe if you found this useful, and see you in the next video.